Hi students, this topic is about two different topics or two different concepts we are going to discuss today. One is lethal genes and another is epistasis. The both topics are part of the unit of genetics. So we are going to discuss about them today. First is the definition of lethal gene. So any mutant gene that results in the death of the individual either in the prenatal, that is before the birth, or the postnatal period, that is after the individual is born, but before or prior to sexual maturity. So any mutated gene, or you can call it as a damaged gene or affected gene, which leads to or results in the death of an individual who carries those damaged or mutated genes in the embryonic stage during the development, that is prenatal before the individual is born, or even if the individual gets birth, the individual cannot reach up to sexual maturity. That type of genes which lead to death is called as the lethal genes. Now there are different types of lethal genes depending upon the types of alleles we see. So we have dominant lethal, we have recessive lethal, and we have intermediate lethal, also called as sublethal or semi-lethal genes. So we are going to discuss about this type of different type of lethal genes and lethal alleles one by one. So the first one is dominant lethal. If death is caused by two dominant genes, then the said genes are referred to as dominant lethal. If dominant, so obviously it is in the homozygous dominant state. In heterozygous dominant, they won't be expressing themselves. If they are in homozygous dominant state, if both the alleles are present in homozygous state, they will express themselves and the individual will die. So basically, if there is a cross, if there is a cross between two heterozygous individuals, sorry, each having a dominant allele, which express itself only in homozygous conditions. See, this is an exception. Normally, dominant alleles express themselves even in heterozygous condition. But in case of lethal gene, in case of dominant lethal gene, they have to be present in homozygous dominant state. So the parents are going to be heterozygous, obviously, because they are sexually mature and they are reproducing. And the ratio which we get, instead of getting 1 is to 2 is to 1, we get an exceptionally different ratio, that is 2 is to 1. Now a Mendelian ratio is 1 is to 2 is to 1 or 3 is to 1. Normally what we see, for example, if you look at the Punnett square, if you make a Punnett square, let's say we take this as the male and over here the female, and as both the parents are heterozygous, we are going to get the alleles in the gametes distributed equally. So we are going to get one genotype of homozygous dominant, two individuals with heterozygous dominant genotype, and one individual with homozygous recessive genotype. So this, in a normal case, in a Mendelian case, it will be 1 is to 2 is to 1. One homozygous dominant, two heterozygous dominant, and one recessive homozygous. But in case of dominant lethal genes, the one where the dominant alleles are present in the homozygous state, the individual dies. This is in case of this example is seen in case of coat color in mice. In case of coat color of mice, the mouse which has both the dominant alleles, the individual will die. The one with heterozygous dominant will give you yellow color, and the one with homozygous recessive will give you brown color. So I can show you a picture of it. This is what happens. So if there is a homozygous dominant state, the individual will die. In case of heterozygous dominant, you'll get the yellow color coat. In case of homozygous recessive, either white coat or brown coat. So homozygous recessive is surviving over here, but the homozygous dominant is dying. As the individual with homozygous dominant is going to die, it is the dominant lethal genes which are responsible for the death of the individual. Okay, and remember that the ratio what we get is 2 is to 1 and not 1 is to 2 is to 1. Okay, so this is an exception over here for Mendelian genetics. So remember, this could be a question asked. This could be a very good MCQs. What is the ratio in case of dominant lethal of the offspring? Okay, what could be the what is the ratio of the dominant offspring in the dominant lethal? Now let's see another type of lethal gene, that is the recessive lethal. Over here, the death of an individual is caused by presence of two recessive genes, recessive alleles. So, for example, if the recessive or now over here there's no exception that the recessive are there, so obviously recessive express themselves only in case of homozygous status. So in case of homozygous condition, only they will express themselves, but in case of heterozygous condition, the parents obviously they are going to be heterozygous, so they are not going to they are not going to express the character. The individual will survive, but the individual with the uh, homozygous recessive condition won't survive. So over here, the ratio will be 1 is to 2. 1 is to 2. 1 with homozygous dominant and 2 with heterozygous dominant state. Let's see, this will be like, if I give you an example, example of the gene which is responsible for adherence of lungs in case of humans. Now, the parents are heterozygous, obviously. We will make a Punnett square again. This will be male or the father. Over here will be the female or the mother. And let's say the heterozygous condition, so gametes will be uh, distributed equally. So we'll have one homozygous dominant, one and two heterozygous dominant, and one homozygous recessive. The person which will have this gene, homozygous recessive gene, a homozygous recessive pair of alleles, this will die. And that is the reason we have 1 is to 2. 1 is to 2. The ratio in case of recessive lethal will be 1 is to 2. Remember this, it will be 1 is to 2. Okay, so you can see over here in case of mouse also, this is one of the example. The individual which have homozygous dominant will have agouti coat. The individual with heterozygous dominant will give you yellow coat, and the individual with both the homozygous recessive alleles will die. So the ratio will be 1 is to 2. So 2 is to 1 for dominant lethal and 1 is to 2 for recessive lethal. Let's move ahead. Now we come to another type of lethal genes, that is the intermediate lethal. These genes do not cause death. They don't cause death actually, but they cause deformity. So if we talk in a definition, genes when genes are present in heterozygous condition and lead to deformity and not death, they are called as intermediate lethal or semi-lethal or sublethal also. So they don't cause death, but they cause deformity, and they are present in heterozygous condition, not in homozygous condition. Now, as they are present in heterozygous condition, they are not expressed completely, but if they are present in homozygous condition, they will become dominant lethal. If they are present in homozygous condition, dominant lethal. Okay, and as we have seen till now, the parents will be heterozygous, and these heterozygous parents will also be the like they won't be carrier, but they will be affected. So there's one example in case of chicken. The chicken which has bended legs, those legs which are bended inwards, and because of those inward bended legs, they can't run very fast. Those type of chickens are called as creepers. So there's an example, and the reason for it, there's one gene for the bending of the leg. Okay, that is called as the L. So chicken leg with bended will be the lethal one, and with small n will be the normal one. So we'll have normal and lethal. And if the uh, genotype is this way, heterozygous dominant, one lethal allele in combination with one normal allele, heterozygous dominant, the offspring will be creeper. So let's see what happens over here. Let's make a Punnett square again. There's a male and a female. So over here, the gene for or the allele for the uh, lethal allele is dominant over here, but it does not express itself in the dominant condition, because in the dominant condition, what will happen if both of them are present in dominant condition, the individual will die. But it will express itself in heterozygous condition also, but not leading to death of the individual, but only deformity. So this individual becomes creeper. Even this individual becomes creeper, and the individual which gets both the normal allele will have normal type of legs. So even two heterozygous parents, two creepers can give. There is a chance of giving birth to one normal. There's probability of giving birth to one normal individual. So the probability over here will be 2 is to 1, but this two will be affected. They both will be creeper and one will be normal, and one will die because these intermediate lethal genes are expressing themselves in the homozygous dominant state. That is the reason this lethal gene is dominant. So it is expressing itself in homozygous dominant. The major difference between intermediate lethal and dominant lethal is dominant lethal was expressing itself only over here. It was not expressing in the heterozygous condition. But intermediate lethals, they express themselves in heterozygous condition also. May not lead to death of the individual, but they cause deformity. That is the reason they are called as intermediate lethal. They cause deformity. Whereas dominant lethal does not cause any kind of deformity. They express themselves only in case of homozygous dominant state. So that was about different types of lethal alleles and lethal genes. So we saw that dominant allele which causes 2 is to 1, which gives us a ratio of 2 is to 1, as well as intermediate lethal which gives us the ratio of 2 is to 1, which is exception to Mendelian ratio, because one of the individual, one of the offspring cannot survive either in dominant lethal or recessive lethal, or even in intermediate lethal. Wherever there is a homozygous stage, the offspring does not survive. So remember this. This could be a very good MCQ. Wherever there is an homozygous state, either dominant or recessive, or even in case of intermediate lethal, the offspring does not survive. Okay, so this was about lethal alleles and lethal genes. Let's move ahead to the next concept, that is epistasis. Now, basically, epistasis is when genes interact, uh, and the interaction of the genes affects means one of the gene, one pair of the gene, when they express themselves, their expression affects, in a way, mask or hides or modifies the effect of another gene or another pair of genes. So see, the genes are affecting means they are not like working in solitary. They are not like individually, or they're working independently. They are affecting each other's expression. And when, if it is positive, it's okay. But when it is negative, when one of the gene, let's say for example gene 1 and gene 2, when gene 1's expression mask the expression of gene 2, see, they are not alleles, they are different genes, that altogether different genes are responsible for different characters. But when the expression of gene 1 mask or modifies or you can even delete the expression of gene 2, that type of behavior in between two genes or interaction in between two genes is called as epistasis. And the gene which is masking or hiding or modifying the action of another gene is called as epistatic gene. The gene which is modifying is epistatic gene, and the gene which is getting masked by another gene or modified by another gene is called as hypostatic. Epistatic and hypostatic. So this is basically a very important. See, this is not dominant or recessive over here. It is like one gene affecting action or expression of another gene. Earlier, what we see as one allele affecting the expression of another allele, or one same gene. Okay, but now we are seeing two different genes altogether. They are affecting. These genes may be present in different locus, in different. So they may present in different chromosome in different loci. Okay, we have 22 pairs of chromosomes. Let's say, for example, gene 1 is present in chromosome number 5, gene 2 is present in chromosome number 7. But presence of the gene does affect the another gene. Or they may be present in the same chromosome but different locus or different location. Locus means location. So, in case of epistasis also, we see there is different types of epistasis. We see dominant epistasis, we see recessive epistasis, as well as we get to see double dominant epistasis and double recessive epistasis. So see students, till now in case of lethal genes and lethal alleles, what we saw was a monohybrid cross because there was only one gene, alleles of one gene. So now as we are seeing two different genes, we have to see the examples in dihybrid cross. So we have to make the Punnett square like likewise. So the first example of dominant epistasis is when the dominant allele of one gene, the dominant allele over here, whether it is a homozygous condition or heterozygous condition, it doesn't matter. If a dominant allele is present of one gene, it will mask the expression of another gene. This type of epistasis is dominant epistasis. So it could be like the gene may be homozygous. This is the sorry. If the gene may be homozygous dominant or it may be homozygous heterozygous dominant, but it will mask the expression of another gene. So let's see a Punnett square. If you draw a Punnett square, so instead of the normal Mendelian ratio, what do we get? In case of dominant allele or dominant epistasis, even over here, the parents will have heterozygous kind of a genotype because if they are homozygous and if they are homozygous, they are going to, I mean, there may be a possibility that they also have the masking of the gene. So let's say if the parents are heterozygous and heterozygous, let's say if this is one of the inhibiting gene, okay, and this in case of F1 generation, we have the genotype like this in case of the mother and same in case of the father. Okay, so now what type of the gametes do we get? Let's say Punnett square over here. So we get the gametes like capital I, capital B. We get capital I, small b. We get small I, capital B. We have small I, small b. Similarly over here, same type of combination of the alleles, same type of the combination of the alleles. This is because both the genes are present on the same chromosome, maybe on different locus, but on the same chromosome. So during segregation of the chromosomes, they are staying together. So what will happen? See, this is an example. I'll give you an example of the in case of dogs, white dogs mated with black and brown coated dogs. Okay, so over here, what we get? we'll get a genotype of capital I, capital B, capital B, capital I, capital B, small b. So over here, both the genes are homozygous dominant, and over here will be heterozygous. So if both of them are white, when they are white dogs are mated. Okay, so capital I, small I, capital B, small b. So I'll just make it quickly. Okay, so now over here, only two of them are homozygous over here. All of them are in heterozygous condition. So we have homozygous dominant of both the genes. So we have homozygous dominant and homozygous recessive over here. So we get the phenotype over here will be white, because in heterozygous condition, if they are expressing the character white, again the effect will be white. So even over here will be white. Progeny will be white in color. Again, the progeny will be white in color. Now something different happens. Now what happens over here, we can see that in absence of a dominant allele, the phenotype varies. Now, if you see, these are two different genes. Capital I means I and B. They are alleles of different G. Whether it is capital I or small I. Capital I is the dominant allele, small I is the recessive allele. Capital B is the dominant allele, small b is the recessive allele. And both the parents were heterozygous for both the genes. Both of them showed white color. So most of the offspring were giving white color, but in absence of a dominant allele of I, in presence of a homozygous recessive genotype of I and homozygous dominant of capital B, the phenotype was black in color. The same was the phenotype was black, but the genotype of the B was heterozygous dominant. Uh, Now, what do we see over here? In absence of the allele, a dominant allele in one of the gene, a new character is expressed. So you see black colored babies in three progenies with black color and one with brown. So if we make the uh, we make the ratio, we'll get 12 is to 1 is to 1. Okay. 12 white, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 white, and sorry, not 1, it will be 3. 12 is to 3 is to 1. 12 is to 3 is to 1, which is still again a very different one. Normally, in case of Mendelian ratio, what we get is to 9 is to 3 is to 3 is to 1. But over here, even in case of dihybrid cross, the dihybrid cross in Mendelian Punnett square used to give us 9 is to 3 is to 3 is to 1. But over here, what we get is 12 is to 3 is to 1. This gives us a very clear view that one of the gene is masking the expression of another gene. So till, and it also in case of dominant state, whether it is homozygous or heterozygous. So if it is homozygous, it is going to it is going to mask the expression of another gene, as well as in case of the heterozygous condition, it is masking the expression of another gene. In absence of a dominant allele, another gene expresses itself. So in absence of a dominant allele, another gene expresses itself. So that is the dominant epistasis, where one gene, whether in case of homozygous or heterozygous condition, must the action of another gene. Now let's see another type of epistasis, that is recessive epistasis. Over here, the recessive alleles at one locus in homozygous. Now over here in homozygous condition only, they will prevent the expression of alleles at another locus, and this is called as recessive epistasis. So exactly opposite to the dominant epistasis, where whether in homozygous or heterozygous condition, the dominant allele is going to mask the dominant gene is going to mask the expression of another gene. But over here in recessive epistasis, one of the condition which is mandatory is that the epistatic gene should be in homozygous condition. Okay, so it will act only in case of homozygous condition, because they are responsible for they are responsible for masking the character of another expression of another gene. So let's see, for example, over here again, we have to take the let's say, for example, the genotype of the parents. So it won't be heterozygous, it will have a homozygous condition. Say we have the parent, let's say CACA. C is for the character of, means, it is like a homozygous black mouse, and we have a homozygous albino mouse. Okay, so CC is responsible for black color and AA is responsible for albino color. So what we will get in the F1 generation will be a heterozygous condition CCAA, and this mouse will be agouti. It won't be black or it won't be white. This will be agouti mouse. So if we mate the agouti mouse, if we made the F1 generation, if we go for the F2 generation, uh, this mouse will give us, if we go for self cross of F2 generation, an agouti mouse along with an agouti mouse. So what type of the gametes we will get? CACA, we get small c, capital A, small c, small a. Similarly over here, CACA. So let's do it quicker. Now we have the same type of genotype, a normal dihybrid cross two characters at a time we are considering. Well, let's see the phenotype of it. As both the dominant alleles are present, they are going to mask each other, they are going to affect each other, so the color will be agouti. Homozygous dominant condition, over here was heterozygous dominant condition, so homozygous dominant condition agouti. Again, here will be agouti. Let's see AG for agouti, again AG for agouti. So you see, wherever dominant allele is present, over here, as the gene for black color is dominant, obviously it will be black, agouti. As dominant is black, so obviously it will be black. One of the gene is in heterozygous condition, so obviously agouti. The albino means the white color, or the albino genes are over here homozygous dominant, so uh, albino over here will be agouti, it will be black, it will be albino, and over here now see both of them are homozygous recessive, still they will be albino. Okay, homozygous recessive, still they will be albino. Now what happens over here is uh, the gene responsible for the coat color, even if it is in homozygous condition, recessive condition, it will mask the uh, coat color of another, it will mask the coat color, or it will mask the expression of the gene responsible for black color. Okay, it will mask the gene responsible for black color, and because the other gene is also in the homozygous recessive condition, it won't express itself. So one of the requirement is that in case of the recessive epistasis, both the gene which is been uh, repressed, or the hypostatic gene, the hypostatic gene should be in homozygous recessive condition, as well as the epistatic gene will be in homozygous recessive condition. So in case of homozygous recessive epistasis, the hypostatic gene has to be in the homozygous recessive condition, because if it is in if it is in heterozygous dominant condition, it won't be expressed. So it won't affect if it is in heterozygous condition, unless and until the hypostatic gene is homozygous recessive. The epistatic gene won't hide or won't mask the hypostatic gene. So that was about the recessive epistasis. Let's move to double dominant epistasis. Now, in case of double dominant epistasis, now what happens? The two dominant genes at two different locus. Now, these are homozygous dominant or heterozygous dominant, doesn't matter. They are epistatic to each other. So, let's say, for example, the feathers in the shank region of the chicken. Now, two dominant genes present on two different loci, whether in homozygous or heterozygous doesn't matter, but they will affect each other's expression. So, for example, in case of chickens, two different genes, let's say capital A, capital S, capital B, these are homozygous dominant. If they are present, the chicken leg will have feathers, and in case of heterozygous or homozygous recessive, unfeathered. Feathers on the shank means on the legs, and unfeathered means absence of feathers on the shank or the leg. So the F1 generation will be heterozygous dominant, and all the progeny will be feathered. All of them will be feathered. If we uh, have a cross of the F1 generation to get the F2 generation, uh, so if you have a cross with heterozygous dominant of the F1 generation, the F2 generation will have, instead of giving us those 9 is to 3 is to 3 is to 1 type of ratio, we'll get 15 is to 1 ratio of phenotypic ratio of the uh, character. So we'll have the same type of a Punnett square, a dihybrid cross over here, and as we have two different genes with two different alleles, heterozygous condition. So let's see what type of gametes we get. We have capital A, capital B. We will be having capital A, small a, capital B, small a, small b. So similar over here, and we'll see what will be the genotypic ratio and what will be the phenotypic ratio. So genotypic ratio remains same all over here, but the phenotypic ratio varies a lot. So capital A, capital B, capital A, capital B, small b, capital A, small a, capital B, capital B, uh, capital A, small a, capital B, small b. Now here the genotypic ratio remains same, that is 1 is to uh, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we'll get the same type of genotypic ratio, but the phenotypic ratio varies. Uh, Over here, this dominant homozygous dominance of both alleles, so obviously they will be feathered. Over here again, as homozygous dominant, heterozygous dominant, again they will be feathered. Wherever a dominant gene is present, they are going to be feathered. Okay, even if even if one of the gene is homozygous recessive, still the character will be expressed. It will be feathered. Will be feathered. Over here, if even if one of the gene is homozygous recessive and the other one is heterozygous dominant, still the character will be expressed. Like say for example over here, this is capital is small a, that is heterozygous dominant. This is small b, homozygous recessive. Still the character will be expressed. This gene will mask the character of this gene completely, even in heterozygous condition. Same feathered. Now, similarly, homozygous recessive, but homozygous dominant, so feathered. Homozygous recessive, but heterozygous dominant, so feathered. Again, same feathered, feathered. Now, over here, both the genes are in homozygous recessive condition. Both the genes have homozygous recessive alleles. So now, this progeny won't have the feather. So this will be unfeathered. So now, what type of ratio do we get? Phenotypic ratio do we get is 15 is to 1. So this is very important, the exception in the Mendelian genetics in case of double dominant epistasis. And in case of the recessive epistasis, I forgot to tell you, the recessive epistasis, instead of giving us those 9 is to 3 is to 3 is to 1, we get 9 is to 3 is to 4 type of ratio. Okay, in case of recessive epistasis, we get to 9 is to 3 is to 4. So let's see, this is about double dominant epistasis. Let's see another type of epistasis, that double recessive epistasis, exactly opposite to double dominant epistasis, when two recessive genes at two different locus, only in homozygous condition. See, recessive to homozygous condition is a mandatory uh, thing, and if those homozygous recessive alleles or genes are epistatic to each other, it is called as double recessive epistasis. Now, see, let's see, for example, the uh, in case of human beings, uh, if the alleles are present in homozygous recessive condition, two different genes, say for example, small b, if the genotype is, let's say for example, small a, capital B, small b, that is the heterozygous dominant, or let's say for example, capital A, small b, or for example, capital A, small b, or for example, capital A, small a, capital B, small b. All of them, uh, or small e, all of them will give the same phenotype. Same phenotype. So this is exactly opposite to the double dominant epistasis. Over here, the homozygous recessive condition in the genotype uh, will mask the expression of the dominant allele. This is very opposite to what we have learned till now. We have seen that the dominant allele masks the expression of recessive allele, but over here, in the double recessive epistasis, the genes if present in homozygous recessive condition, they will mask the expression of other uh, gene if present in homozygous recessive condition. They will mask the expression of other gene. Now, this is condition in case of humans are deaf and mute, those children who cannot listen or they who cannot speak. Their genotype may be either small a, capital B, small b, or small a, capital B, or it could be capital A, small b, small b. So, if two deaf and mute people with a genotype of capital A, small a, capital B, capital B, and capital A, small b. Both of them, as it is the double recessive epistatic condition, both of them will be deaf and mute. But in the F1 generation, because there will be a heterozygous condition, there won't be a homozygous recessive condition over here. The baby will be normal, will have a normal hearing capacity. Then let's see what happens if a normal baby mates with another normal person who also has heterozygous condition. So let's make a Punnett square of this again. Again, dihybrid cross we have to see the type of let's say, because we are going to match with heterozygous condition. So capital A, capital B, capital A, small a, capital B, small a, small b. Let's do it quicker. So now, what we get, as they are homozygous dominant, both of them will be normal. As there is homozygous dominant, heterozygous dominant will be normal. Heterozygous dominant, homozygous dominant, normal. Again, same, normal. Over here, what we see, normal hearing. Now, what comes over here is homozygous recessive condition. So this individual, this offspring, will be deaf and mute. Same heterozygous dominant, so normal. Same thing happens over here. Homozygous recessive conditions comes over here, so this offspring will be deaf and mute. This is normal. Again, heterozygous dominant, normal. Again, homozygous recessive alleles of one gene comes, so deaf and mute. Again, homozygous condition, deaf and mute. But heterozygous normal, dominant, normal. One more homozygous recessive, so deaf and mute. One more homozygous recessive, so deaf and mute. Now, this will be obviously deaf and mute. So, if you look at the phenotypic ratio out of the 16 individuals, so 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 will be normal, and rest of the 1, 2, 3, 4, 5, 6, 7. 7 will be epistatic or hypostatic, affected. So the ratio of the double recessive epistatic over here will be 9:7, and in case of double dominant we saw was 15:1. So here the affected number increases in case of double recessive epistatic. So again, a very good question. Uh, in which of the following type of epistasis the number of affected are more? We have four choices: dominant, recessive, double dominant, or double recessive. So obviously, double recessive gives you more number of affected because the homozygous recessive, wherever homozygous recessive uh, alleles come in one of the gene, they mask or they hide or they suppress the expression or the action of another gene. So that leads to again the type of deformity, type not deformity but type of condition what we come across. That is the deaf and mute condition in case of humans. So what have we learned from all this discussion? See, mutated genes are filtered in natural selection. So, in case of lethal genes, the mutated genes are filtered in natural selections. So, those individuals which have those mutated genes or those damaged genes, they do not survive till reproductive age. So if they do not survive till reproduction, they do not survive the sexual maturity, they won't be able to reproduce. So if they are not able to reproduce, they won't have progeny, and so those mutated genes won't go ahead in the population. So those mutated genes won't be propagated in the population. That is how nature works. And then we discussed that the genes affect the expression of each other. So we have seen in case of epistasis that the genes they do affect expression of each other. They have an effect on another gene as well. Either they could be we are not going to that much of molecular level, but it is that like one of the gene which is affecting the epistatic gene may be a gene responsible for a particular enzyme or a particular precursor which activates the hypostatic gene. So if in case of double dominant or in case of dominant or recessive, uh, the action of the epistatic gene, if not either activated or non activated, affects the action of the hypostatic gene. So that was about lethal genes and epistasis. We'll discuss about this in the lecture. Thank you guys. Thank you very much.